Hi everybody, and welcome to lesson 4.7, Aquatic Pollution. The content in this video is aligned to the third edition of Environmental Science for AP and is aligned to CED units 8.1, 8.2, 8.7, 8.8, and 8.11. Here is our content objective for this lesson. Human activities, including the use of resources, have physical, chemical, and biological consequences for ecosystems. At the end of this lesson, you should be able to identify differences between point and non-point sources of pollution, describe the impact of human activities on aquatic ecosystems, describe the effect of persistent organic pollutants, POPs, on ecosystems, describe bioaccumulation and biomagnification, describe the effects of bioaccumulation and biomagnification, and define best practices in sewage treatment. All of this is leading us to answer our guiding question: how should we manage aquatic pollution? To begin, let's look at the general categories of aquatic pollution. By definition, aquatic pollution is anything that can be carried or dissolved in water that causes a decrease in water quality. We typically look at aquatic pollution as being either solid, organic, inorganic, or thermal. By sorting different aquatic pollutants, we can explore sources and provide some categorical potential solutions to these problems. Solid waste is anything that does not dissolve in the water. It can be carried on the surface or in deeper currents throughout it. Common examples of solid waste in this instance include natural debris such as limbs and leaf litter, and trash, which includes plastic, glass, and other human-produced compounds. Organic waste is waste that is carbon-based, such as human and animal feces. These compounds require living organism metabolisms to break them down, which can use a large amount of dissolved oxygen in water. Organic waste is often responsible for eutrophication in the formation of dead zones, or areas of very low dissolved oxygen. Additionally, a class of compounds called persistent organic pollutants, also known as POPs, are often found in water. We will discuss these in more detail in our lesson on human health. One of the things to note here is that POPs tend to be fat-soluble, which increases the chances that they will bioaccumulate in a single organism and then biomagnify up the food chain. Inorganic compounds, such as NPKs and phosphate soaps, can contribute to eutrophication and increased turbidity. Lastly, we have thermal pollution, which we have discussed previously as being associated with nuclear power generation. Thermal pollution can contribute to eutrophication and vast fish kills due to extreme changes in temperatures, a process known as thermal shock. Here we see a series of pollutants that are common in water sources around the world. Some of them are more common in different areas, but they are worth discussing as they have serious impacts on the potability or drinkability of water. 3 of them are naturally occurring heavy metal compounds: lead, arsenic, and mercury. Lead is often introduced into water supplies through the use of metal in pipes. When exposed to acidic water, lead will degrade and become suspended in the water. This is exactly what happened in Flint, Michigan in 2014. The switch to a new water source, the lack of treatment of the water to neutralize its pH, and outdated plumbing systems provided the perfect storm to introduce large amounts of lead into the drinking water. 7 years and hundreds of deaths later, the city is still dealing with this problem. It is a prime example of environmental racism, as Flint has a very large African American population. Arsenic is a byproduct of the breakdown of some rock types and is more likely to be found in well water than treated water. Deeper aquifers are more likely to be contaminated by arsenic than those that are closer to the surface. Petroleum exploration is a common source of inorganic mercury, which seeps into water sources and is converted by living organisms into methylmercury, a highly toxic substance that bioaccumulates in the bodies of fish, particularly predatory fish. Asia has the largest concentration of mercury emissions, a problem that makes it difficult for seafood from Asia to be sold in other countries, as the seafood is highly concentrated with methylmercury. Acid deposition occurs in the form of acid rain and emissions from industrial smokestacks. Pesticides run off from nearby farms. The inappropriate disposal of medication leads to concentrations of steroids and other hormones in the water. Many people will either throw away or flush leftover medication, which can lead to large amounts of problems for other humans and organisms in the water. By the way, you can return any unused medication to your local pharmacy for appropriate disposal. Lastly, there are industrial compounds such as perchlorates, which are components of jet fuel, and polychlorinated biphenyls, or PCBs, a common component of plastic manufacturing. PCBs and perchlorates enter water resources and sometimes mix with settled sediments, making them very persistent in the ecosystem. In order to understand the impact of these aquatic pollutants, it's important to understand how we measure water quality in general. Here are 11 of the most common and most important values that are explored for determining water quality. Note that this is not a definitive list, and we will see some other compounds that are tested for in the next slide. Let's go through these in detail. Turbidity is the measure of clarity of the water. Highly turbid samples are those that are cloudy and dark, often having a large amount of dissolved and suspended materials. These suspended materials are often silt or other naturally occurring compounds, although things such as microplastics can be found there as well. Highly turbid water samples often have very low photosynthetic rates due to the lack of sunlight penetration. Turbidity is closely associated with flow speed, as more stagnant water is more likely to be highly turbid than that water that is highly modal. Salinity is a measure of the dissolved salts and associated ions in a sample. Remember that fresh water does have a concentration of salt, but it is significantly different than seawater. It's important to note that various areas will have various measures of naturally occurring salt contents. There is no universal measure for acceptable salt, with the exception of water that is used for human consumption. In nature, comparative sampling is essential. Salinity is also associated with conductivity, as a large number of ions can help to contribute to the movement of electricity in water. Total dissolved solids, or TDS, is a measure of the number of compounds that are dissolved in the water. This can be related to turbidity, conductivity, salinity, and pH. pH, as we are well aware, is the measure of the proportion of hydrogen ions and hydroxide ions in an aqueous solution. This, like salinity, is something that requires comparative sampling, as different areas are likely to have varying pH measures based on surrounding area conditions. Temperature is closely associated with dissolved oxygen, DO, and dissolved carbon dioxide, DCO2. Note that the relationship for these gases and temperature is an inverse relationship. As temperature drops, the ability of water to hold DO and DCO2 increases. Simply stated, this means that cold water typically has a higher DO or DCO2 than warmer water. DO and DCO2 are measures of specific gases that are found in the water. These gases are vital for organisms such as fish and bacteria to go through the process of cellular respiration. Both measures are also closely related to biological oxygen demand, or BOD. This is the amount of oxygen a set of organisms is using in a particular location. We will take the time to look at a BOD graph and explore those components. Lastly, fecal coliform bacteria are microorganisms that are found in the feces of living things. They grow well in aqueous solutions and can often carry numerous diseases. They are largely found in areas near animal husbandry and feedlots. Taken together, these measures can tell us a good amount about water quality. Additionally, we can use what are known as indicator species to determine the health of the ecosystem. We'll discuss more about indicator species in Unit 5. This is a set of data that looks at guidelines for components that should be evaluated for a particular water sample. Water quality index values are measured by using the raw data, such as the pH or dissolved oxygen, and using a set of graphs that provide what are known as Q values. These Q values are added together to provide a water quality index. A sample of a Q value graph can be seen on the right. Note that it is used to determine the suitability of the sample for drinking, or determining if the water is potable or not. While this can be used to measure water quality for locations not identified as drinking sources, it's also relatively high quality related to the values of indicator of water quality. meaning if a natural source meets the conditions for potable water, it's a pretty healthy and clean resource. We know that dissolved oxygen is an incredibly important component of the health of an aquatic ecosystem. We also know that biological oxygen demand is the value of how much oxygen is used at any given time in any given sample of water. It's logical to say that when dissolved oxygen concentration is high, the biological oxygen demand is typically consistent and relatively low. As the number of organisms in the ecosystem increase, the use of oxygen increases. The general pattern is that BOD and DO are inversely related to one another. The diagram shown here shows the relationship between these measures in a body of water after a discharge of a high amount of organic material. Note that the introduction of the organic material kick-started the BOD, which rapidly depletes the dissolved oxygen. As more of the organic material is decomposed, oxygen continues to decrease until the living organisms in the area become stressed and typically die off. At some point, the dissolved oxygen will reach a level that is so depleted that the remaining organisms cannot carry out cellular respiration. BOD drops significantly, which allows dissolved oxygen to recover to the previous concentration. Here is that same graph applied to a river system with living organisms. This application allows us to break the process down into 5 separate zones that exhibit particular characteristics in relation to the BOD and DO in the area. The first zone is pre-pollutant. This is called the primary clean zone. This has a high dissolved oxygen and low biological oxygen demand with a wide variety of normal aquatic organisms. Once the pollutant is introduced, we enter the decomposition zone. Here, BOD increases substantially, leading to a relatively quick drop in dissolved oxygen. This zone typically has fish and other organisms that are generalists and can survive in areas of lower dissolved oxygen. The continued decomposition of the pollutant moves us into the septic or anoxic zone. In this zone, the dissolved oxygen is at its lowest, but the BOD is also starting to drop. There are few organisms living in this area. Most of them are anaerobic organisms like bacteria, and some worms and leeches. Next, we move into the recovery zone. This is similar in terms to organisms in the decomposition zone. However, here, the BOD is low and the dissolved oxygen is beginning to increase. Finally, in the secondary clear zone, the BOD and DO have returned to their primary conditions. This process is known as an oxygen sag curve. As we move forward, particularly into Unit 5, think about how the location within the water would provide widely varied measures of those water quality conditions and how that might impact how we would make decisions about remediation or future mitigation. Let's discuss the major components of aquatic pollution that come from human sources. These are broken down into 3 separate categories: surface runoff, stormwater runoff, and wastewater. Surface runoff occurs when water cannot infiltrate soil due to an excess of impermeable surfaces. The water is often contaminated with things such as oil or gasoline that has leaked from a car, solid debris like trash and fallen leaves, or other components. In cities and towns, this water is sometimes collected in culverts that direct the water either to a sewer or to a nearby body of water for discharge. The same occurs with stormwater runoff, which is an excess of rainwater due to impermeable surfaces and inadequate drainage. Lastly, there's wastewater, which is a mixture of what we know as gray and black water. This comes from homes and industry and is treated either in sewage treatment plants or through the use of a septic tank. Let's take a moment to define our terms. Gray water is water that comes from sinks, dishwashers, showers, and other locations that are not subject to harsh chemicals or human waste. This water can often be repurposed for watering plants or washing your car. It definitely isn't potable, but it can be used for other purposes. Black water, on the other hand, is water that comes from toilets or other locations that are subject to harsh chemicals. This water is expected to be treated at a plant or through septic disposal. Here you see a traditional parking lot on the left and a permeable parking lot on the right. The traditional lot uses asphalt, a byproduct of fossil fuel distillation, and a heavy sealant to provide a surface that will handle large amounts of traffic. Unfortunately, these surfaces make it impossible for water to seep through to the soil beneath. These kinds of large paved lots contribute significantly to surface runoff. On the other hand, the use of permeable parking lots, which often use interlocking bricks or a combination of bricks and sand, allow water to infiltrate through, reducing the amount of surface runoff and the introduction of oil and gasoline into nearby water sources. The next problem to address is stormwater runoff. One way to address this is through the sewer system. There are two basic types of sewer systems, a combined system or a dedicated system, which is also known as a sanitary sewer. Note that the immediate difference is that the combined sewer system uses the same pipes to transport sewage and stormwater, which can easily lead to the volume of water exceeding the amount of water the treatment plant can take at one time. Any overflow is released into the nearest body of water through an exit pipe. This overflow could include both stormwater and untreated sewage. A dedicated system, or a sanitary system, is different in that it has two separate pipe systems. One is used exclusively for sewage, while another is used exclusively for stormwater. The sewage is taken directly to the treatment plant, while the stormwater is directed to a nearby body of water for release. This is the general process associated with a municipal wastewater treatment plant. A typical plant has two general processes, primary and secondary treatment. Primary treatment is purely physical, while secondary is biochemical. The purpose of primary treatment is to remove large debris and suspended solids from the water. There are three steps in primary treatment. The water enters the plant through an influent pipe and reaches the first stage, which is bar screening, where the water is put through a wide mesh screen to remove large floating debris. Then the water moves into the grit removal stage. Here, the water is allowed to settle and smaller mesh screens are moved through the water. Solids precipitate out and are pumped to a sludge chamber. The water then moves to the primary clarifier, or the primary settling tank. Here, the water is left to settle for a significant amount of time, though it is stirred every now and then. Here, solids precipitate out and are pumped to the sludge chamber. After this stage, the water has completed primary treatment. Secondary treatment begins with the aeration stage, where oxygen, bacteria, and a component known as activated sludge are added to the water to increase the rate of breakdown of organic waste. Bacteria and other small organisms are allowed to carry out a variety of processes that remove the organic matter from the water. After aeration, the water is sent to the secondary clarifier, or the secondary settling tank. This is a repeat of the primary settling tank. Any remaining solids or suspended compounds precipitate out and are carried to the sludge chambers. The water then moves into the chlorination stage, where it is treated with chlorine, or in some cases, high-intensity UV light, to remove any living organisms still in the water. The water may go immediately to a treatment stage to make it potable for drinking, or it may be released into a nearby body of water through an effluent pipe. Some treatment plants go the further step to apply tertiary treatment, which is specifically designed to remove particular pollutants such as phosphates, nitrates, or medications. Tertiary treatment is incredibly expensive and is only used in a handful of wastewater treatment plants in the United States. The sludge is allowed to dry and is either sent to a landfill or is used as fertilizer on agricultural farms. Lastly, as a general note, remember that wipes do not go in the toilet. Even if it says on the package that it is flushable, trust me, they aren't. They cause big problems with septic systems and sewer pipes as they block vents and screens or coalesce into disgusting mounds of thick fabric that do not biodegrade or dissolve like typical toilet paper. Some people don't have access to municipal sewage systems. Older homes or those that are found outside of a municipality or city often rely on a self-contained septic system. The system is usually made up of a tank and a series of perforated pipes and gravel to filter water. In a typical septic system, the water flows into the tank from the house. The solid material settles to the bottom, leaving water on top. Sometimes there is a layer of scum that is the byproduct of the breakdown of organic waste in the tank. The water is able to flow from the tank through a series of perforated pipes into what is known as the percolation area, a specifically designed area of gravel, crushed stone, and sand that allows the water to be filtered as it infiltrates back into the groundwater. The tank itself needs to be treated and pumped periodically to avoid overflow or backflow. There are several products on the market that introduce microorganisms to the tank to help break down this organic waste and toilet paper. Trust me, you definitely want to keep an eye on your septic tank at all times. Lastly, let's address the regulations associated with water quality. The Clean Water Act is perhaps the most important. It was passed in 1972 and sets requirements for clarity of water in naturally occurring places. It has been amended several times since its inception, sometimes for the better and sometimes more recently for the worse. The Safe Drinking Water Act was passed in 1974 as an addition to the Clean Water Act. It sets requirements for quality and content for publicly provided drinking water. Note this does not apply to individuals who get their water from a home well system. The following slide provides you with an opportunity to see how some of these ideas are connected together. Feel free to pause the video and explore the connections between these topics. Then, use the statements at the beginning to review.